Why water pipelines? So water is one of our most valuable resources. We need it to sustain life itself. And for this reason, humans have developed very fancy ways to take the water from the source and then piped it into the comfy of our homes. When we're doing this, we don't want any water to get loose. So we want to avoid leaks. And in our cities today, there are several organizations that are responsible for the task of taking the water to our homes. In Munich, this organization is called SWM, and together with LMU Munich, we decided to give this task a try. On the left side of this slide, you can imagine the city map of Munich or some abstraction of it with these white circles or nodes representing a microphone attached to one pipeline, recording the relaxing sounds of water running through pipes. So let's say we would have a leak somewhere close to the node or the microphone number 1, then the mic 1 would be able to record this sound, and if some expert would then listen to it, this person would then recognize the leak and would be able to send some other people to fix it. So another thing, possible would be that this leak is maybe between 2 of the mics. So for example, if we have a leak between 4 and 5, then both of these mics would be able to record a sound, and then via triangulation we could be able to locate the leak itself. But before locating any leaks, we need to detect them. Another thing to take into account is that the microphones might be located in different parts of the cities. So some of them might be also close to the highway or close to some transformer house or some fabrics. So definitely there will be some noise in the background that we need to take into account. All right, so to put up with this task, we decided to start with the basics again. We revisited our school material, and remember, sound is actually represented as waves through time in different frequencies. So there's two ways to project this. One of them is to project these waves then through a frame of time, and then we end up having a plot like the one here on the bottom right corner. You might also recognize this from some screens of some supercomputers talking in old movies. Another way to project the sound is choosing a certain amount of time, so a time frame, and then projecting the frequencies into a plane, as in this plot on the right bottom corner. This is called a MEL spectrogram. So we extracted those for us, and in summary, this was our pre-processing pipeline. We got the raw data as MP4s or something, then we cut some snippets of fixed size, and through different transformations got our MEL snippets that looked a little bit like this one here. Although, these snippets are also a representation of matrices, and the matrices themselves were then the input to our machine learning pipeline. All right, so now how does anomaly detection work again in the context of machine learning? Here on the picture, if you're a human, you might already notice that there is an imposter among the cows. But how does then a machine do this? For example, you can extract some features or some features or some characteristics of the objects in the picture as size or amount of tones of brown that this object has, and then project every one of these objects in these terms as a point into the plane. If we do this, we might notice that the cow or the object on the right side is a little bit smaller and maybe has less tones of brown. So we can see that we have some kind of group of cluster being built on the right side, and then the other one seems to be some kind of anomaly. If we would get a new data point, we want to be able to say if this is a cow or an imposter. The way we do this is, for example, by separating the cows from the imposters. For example, here with this hyperplane. In a two-dimensional space, this would be the line. So now for the new data point, if it falls on the right side, we will confidently say it's a cow, and if it falls on the other side, it is probably not a cow. All right, so now for our experiments, we decided to try to use autoencoders to detect leaks. And first, I will explain to you how these autoencoders work on principle. If there are some photographers among you, you might know, you might have a few of these nice, wonderful pictures of yourself that really take up some memory and space. So you might also be familiar with the concept of compressing and decompressing. When you're doing this with pictures, you first compress it to some lower dimensional object like a vector, and then you want to decompress it, and hopefully when you decompress it again, you have as output the same thing that you had as an input, so there is no information getting lost on the way. The idea behind the autoencoder, though, is that when you are compressing and decompressing, there is some information loss. So you might see here that the picture on the right is not as sharp as the one on the left. If we do this for autoencoders, we talk about encoding layers and decoding layers. And these come in basically 3 flavors that we tried out. So there's the simple autoencoder, the convolutional autoencoder, and the variational autoencoder. I will tell you more about this now. So in the simple autoencoder, we had some dense layer only. We tried out with 3 encoding layers and 3 decoding layers, and vectors in between, having dimensions between 3 and 300. You can already see from the pictures that the picture on the right side might not quite look as the MEL spectrogram on the left side. All right, then we also tried some convolutional autoencoders, which also entailed some convolution layers. And we tried between 6 and 18 layers, and the dimensions between 2 and 128 for the vector in between. And again, you can compare the output to the input. Last but not least, we have the variational autoencoder. This encodes the information not to one vector, but to 2 of them. So you have the mean vector and another vector representing the standard deviation. Then both of these are combined so that you have actually one vector at the end before you then decode again. In terms of information, you can say that a simple autoencoder represents some object as a point in a two-dimensional space, while the variational encoder might not only contain information about this point in specific, but also about its neighborhood, since we have the standard deviation and the mean. All right, so after that, we had this machine learning aspect, and this worked as follows. So for the training, we took the input, our input MEL spectrograms, and the ones, for this we used the ones that didn't contain any leak, and what we did is we put them through the autoencoders. The interesting part of the autoencoders is that if the autoencoder already knows the data well, the information loss will be reduced. And then if you give it a picture or an object that it doesn't know, then it will probably not know it as well, and the information loss will be bigger. I will say more about this later. But for the training, what we did is we have then the input, the output, we compare it with each other, then we compute some loss, and using this loss, we then computed some new weights. And with new weights, there comes the new model. After this, we did the classification using the reconstruction error. So what we did now is we took our test data as the files, or the MEL spectrograms corresponding to one file, then we put them through the trained autoencoder and got some kind of prediction. Then we compared the output with the input. Specifically, we then computed the reconstruction error, which in this case was the mean Euclidean distance per frame. With help of this reconstruction error, we then made some classification. So to the human eye, this looks a little bit like this. On the top line, you have the original MEL spectrograms, and on the bottom, you see the reconstructions. And as far as humans can see, you might notice not much of a difference between the reconstruction of the leak and no leak data. But hope is not lost yet, because then we computed the reconstruction errors of two files, one containing a leak and one containing no leak. In this case, it looked a little bit like this. So on the vertical axis, we have the reconstruction error, and on the horizontal axis, we have the snippets. You can first of all see there is some, that we might have zoomed in too much, and you might not, you're not able to see these kind of peaks that we have here. So what we did next, we were curious about them as well, so we zoomed out. It turned out these peaks were quite big. Then we decided also to look more into it. So as you can see here, these peaks then correspond actually to certain parts of the MEL spectrograms. So there must be some kind of another anomaly, or some kind of anomaly that is in there. So as we recognize that exactly in these moments on the MEL spectrogram and in these frames, you were also able to see some difference, we then tuned in. It turned out the first one was, some car then driving over a certain part of the street that was quite loud at night. And the third one that you see here on the bottom was actually some dog howling. All right, but then let's get back to our reconstruction error diagram. So another thing that you might see here is that even though the reconstruction error difference might be a little small, it is still kind of separatable with some kind of threshold. So for this, we decided to use the mean and the standard deviation plus the standard deviation to then compute a threshold that we would use to classify whether in the file there's a leak or there was no leak. In this case, we have for new data, if the file would then have a reconstruction error above the threshold, so kind of like this red line over here, then we would say that's a leak. And if there would be no, the reconstruction error would be then lower than the threshold, like the green one, then we would say, or our model would then predict there's no leak. You can also see that there's some peaks that are already missing that threshold, that go over even though there's no leak. So I will tell you a little bit more about them later. In summary, what we did for the classification with the threshold works as follows. We have the input file snippets, and then we compare them to the output. By this, we then compute the reconstruction errors. We give them some kind of score saying, okay, this is probably a leak if it's high and it's no leak if it's low. Then we average these scores and at the end, we have some kind of value that we then compare to the threshold. If it's above, for example, here, 0.666 is above 0.4, then we have a leak. All right, so how well did we do? We had our, so in order to say how well we classified, we used the confusion matrix. In a best case scenario, you always have the true label on the vertical axis, saying, for example, in here, if there was really no leak, or if there was really a leak in the record that we listened to. And on the horizontal axis, we have the predicted label. So that means, did the model then say there is a leak or not? In a perfect scenario, you have a one on the top left corner and a one on the bottom right corner, and the other ones are 0. As you might already see here, this was quite the scenario for our CNN autoencoder with 2 dimensions. We were also very skeptical when we got these good results, and after looking into how the other models performed, we concluded that our test data set might have been a little bit too small. All right, but in comparison, you can still see here the simple autoencoder, which performed a little bit, worse, right? So here you can see that on the true label in the field of no leak, there were files that were classified as leak and others as no leak. So this is, for example, considering where you would have the autoencoder say there's probably a leak for example, for this green peak that we saw before in the image. and you don't really want the autoencoder to scream there is a water leak every time that your neighbor's dog gets hungry. All right, another way to evaluate this is with the rock area under the curve. So here you see an example again for a perfect scenario. What you want is the area under the curve to be maximized. In the best case scenario, it should be equal to 1. So in the best case scenario, you want it to go up in a vertical and then in a horizontal all the way to the right. Again, the results for CNN were pretty promising, and the results for the simple autoencoder less so. All right, so after 1 week, we decided to pack our successes and to count future work possibilities. So let's start with the successes. After this 1 week, we actually were pretty happy that we got the pipeline set up to run on multiple systems, which took us more work than we anticipated, but at the end, better than getting it to work, we actually documented it. So future generations of these practical courses can then profit from that. Other than that, we got some nice insights into how deep learning methods might be promising for these kind of tasks. And we also got to extract some very exciting knowledge through analysis as, for example, when we had these peaks that I showed you before where it turned out to be an anomaly, but not necessarily a leak on the pipeline. So for future work, what we would have continued to do would have first to improve the single misclassifications as the hungry dog being classified as a water leak. We don't want that. And also what we could profit from is more experiments to maybe then find out that some other models might also do as well in the task. All right, other than that, I also wanted to share with you our tool stack. We used, of course, Python all over, and more specifically, we used some TensorFlow and Keras for the models. We have a GitHub repository available in case you want to check it out. It's this one over here. And as I said before, please just feel free to contact me for questions.